Hello and good morning, guys, to the new organic topic that we are going to start today is alcohols, phenols, and ethers. This is Sudhanshu Tripathi welcoming you for this lecture. And though this is a big topic, but related topic, you will find the flavor will be aromatic in phenols, the flavor will be aliphatic in alcohols, and the phenol will be mixed in ethers, dominating by aliphatics. So you have a mixed feeling, and you have the knowledge of how to handle a benzene ring, how to, well, which is a OP director and an activator, which is a meta director, and a deactivator, which is the opposite type. Both, it is OP director but a deactivator. So these things for ARSC, and in chlorobenzene we had discussed about ARSN, which is very, very rare in aromatics. Aromatics, ARSN, is only possible when there is a minus R group in the orthopara position with respect to the leaving group, chlorobromo. So that, you are wanting to do something for chloro and you have to introduce nitro. What is the fun of doing some changes in chlorobenzene? You have to introduce nitro in orthopara position. So this is therefore not a very popular reaction, ARSN. So, but ARSC is the most favorite reaction of aromatics. Uh, yes, we will take off alcohols, phenols, and ethers to begin with alcohols. So, guys, today, I know you are having a school. Some of you are having school, but Rudra has a school at 9. What time you have school? 10. 10. I know others have a school and other coachings a little earlier, so they will leave. But we will be maybe we'll be extending the class up to 6:45. The portion that you will be missing out, you just discover that in the video that I will send the link, and you prepare accordingly. So you already know the types, just like the types of alkyl halides. You have three types: 1 degree RCH2OH, and of course methanol is the only alcohol which has CH3. That is a primary alcohol. This is primary. This is 2 degrees secondaries, R dash CHOH is known from this, the carbon bonded to OH. And this is 3 degrees, this is 3 degree alcohol. No hydrogen is attached. And, doing about the nomenclature, just to remind you, OH is a functional group, is a type C functional group, and it will get the functional group priority. You cannot leave OH group for selecting the principal carbon chain. Even if it is not the longest chain, you have to consider, you have to take OH hanging onto one carbon of the principal carbon chain. For example, you have a thing like this. Now you have other groups which are of lower priority, and some of them will not have any priority. Type A groups like nitro or chloro, they do not have any priority for assigning the name. So what will be the name of this compound? Can you? Yes. Raise your hand. I am waiting for your hand. You can't ignore the hero. The hero is OH. You can't ignore it. You can ignore
So,
it. You can't. Yes. Any question?
sir, ना sir, कहीं sir,
Hmm?
sir, ना कहीं भी यार.
Oh, yeah, yeah, yeah. Let us not
Sir,
waste time. Hmm.
three chloro, two propyl, pent, four N all.
2-propyl
Pent four N all.
in, and this E will be deleted, right?
Yes, sir.
And what about all? All has a locant. You have to mention that. One all. You told one
One
all?
all.
You told
No,
it?
sir. No, sir.
No, you have to. It's not like carboxylic acid, aldehyde, uh, and the derivatives of carboxylic acid, where the locant one is by default it will be always one, so we ignore writing one. But alcohol, it is variable locant, so you have to mention it.
Yes.
Enoic acid, we ignore one oic acid, but all you have to write. Now see, the longest chain would have been here. One, 2, 3, 4, 5, 6, 7. But we have to be happy with five. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Since there is a double bond here, another functional group type B, so we have to take into account if it is coming under the principal carbon chain. And if there was no double bond here, and you have to also come this way because it is carrying substituent. You have to honor the branching rule. You have to honor the branching rule. Therefore, this becomes propyl. Propyl, and this becomes 1, 2, because all should get the lowest locant, lower locant. 1, 2, 3, 4, 5. So this is 3-chloro, 2-propyl, pent 4 in 1 all. So with little bit of revision, I think there will be no point in wasting time. Then we go for the general methods of preparation, many of which you know. Will not waste our time. Uh, this you know. Simply, I will leave it from alkyl halides. KOH, often it is written aqueous. This is a general, concept in maybe in many books that you have to write aqueous, but many organic compounds are not soluble in water. So alcohol is a definite choice for dissolving organic compounds. But we usually write aqueous KOH. So in that case, you get this compound. This is uh, SN reaction and SN process, and you will get ROH plus KX. And what is the order? The priority order is to 1 degree, 2 degree, and 3 degree. Will go for elimination rather than substitution. We have done vividly elimination versus substitution, all these things we have done. So this is uh, SN2 mechanism operates because OH minus is a very good nucleophile. Being a strong base, it is a strong nucleophile too. That's why SN2. But on the other hand, if you carry out hydrolysis of alkyl halide, it is the opposite. If you just add water to get alkyl halide, it's just to add water to get ROH plus HX. This is the order is 3 degree greater than 2 degree greater than 1 degree, and this is SN1. So 1 degree is very, very slow. 1 degree is very, very slow unless there is a room for rearrangement. So N-propyl chloride or isopropyl chloride. Oh, sorry. If it is 1 degree N-propyl chloride, then there will be hydride shift and you get isopropyl alcohol at the end. But ethyl and methyl alcohol, methyl and ethyl halides, they are very, very slow in hydrolysis because 1 degree carbocation is very unstable, and water has not a very good power of attacking as a nucleophile. It's a weak base. That's why whatever little SN2 will happen, such SN2 is the biggest choice. SN2 for ethyl and methyl halides. So that will be slow. As such, SN2 rate is slower than SN1. Then 3 we will not discuss because I'll give you some SAQs, this what we call a roadmap problem involving all this later to revise. But let me point out, list out the points. Hydrolysis of ester. This is a big, big point. The mechanism we will be doing in carboxylic acid chapter, but here we will be doing the 2 types acidic hydrolysis, where we will be using dilute sulfuric acid, ester, just water is the hero, and this acid will be the catalyst, and here you will be finding OHH. Just I'm writing you this scheme, telling you that water will attack onto the carboxyl carbon. So if this will be labeled, then that will be found in carboxylic acid, not in alcohol that we are studying, because it will attack onto the carboxyl carbon. It is a different type of substitution, not SN1, SN2 or anything related to that. It will be acyl substitution, but nucleophilic. So you will be finding 18 here, and so add as OH. So this is acidic hydrolysis, and we'll be doing the detailed mechanism, how the H plus ion is protonated here, and then the electrophilicity, protonated here, I'm sorry, and then electrophilicity is enhanced, the water attacks, and then pi bond is polarized, then again it comes back, and the leaving group go, and this is again protonated in the third step, and then it comes back, and the leaving group becomes alcohol. The leaving group becomes alcohol. I'm showing you the mechanism. You just to have just, this is the first step that we will have, so that the electrophilicity of this carbon, I'm just telling in haste, that will be done in a very regular manner in our carboxylic acid program. And water is really the nucleophile. It will attack here, and this is the rate determining step. So you get water gets attached, and you have this, and then this proton, this alkoxy group has to be protonated, otherwise it will not be ready to leave. Now these are all reversible processes, so this COH and OH will remain, and this will become protonated. And finally, this comes and this goes as a neutral water molecule. Alcohol molecule, RDAS. RDAS OH is the leaving group. This is the acyl substitution I'm just showing you. RC double bond OH. And this, there will be a plus charge here, and already we have got our compound about which we are studying now. We are now least bothered what is the other product, but since I'm showing you the mechanism, then deprotonation happens here. So whether you write water removes H plus as H3O plus or as H plus, which is not the reality, but often we show H plus just to make the process, I mean, the mechanism look simple. Otherwise, H2O removes H plus and becomes H3O plus. And here in the first step, which I have not written, that ester reacts with H3O plus to be protonated living water. That water now acts as a nucleophile, and then finally water removes H plus and to become RCOOH. So you get carboxylic acid and alcohol. So these are the steps for acidic hydrolysis. The last step is irreversible. That is why it goes, mm, in a irreversible manner. Uh, and then you have alkaline hydrolysis. This is called saponification of ester. By this process, soap is prepared from the triglycerides, fats and oils, and the triglycerides of higher carboxylic acid. So we will talk about that, and I will now tell you that that is why it is named as saponification of ester, because this process was initiated in the preparation of soap by the alkaline hydrolysis of the fats and oils. Now, the mechanism is relatively simple, but the process is a little tedious. You have OH minus, you know, then this will attack, and I will I will show you in a different style. uh, this will go and it will again come, and this will go. As you have seen, the pi bond is polarized in the rate determining step, which is the slowest step, and other steps, though being reversible, but they are not slow step. Now, that is why in one step I used to show the pi bond is, like this arrow, and I saw in one step. I'm not showing you the mechanism. So this is this, and you know alkoxide ion. But since alkoxide ion is a stronger base than alkanoate ion, actually you get a salt. Actually, there is a proton exchange between this, and you do not get carboxylic acid. Instead, you get the salt of carboxylic acid and a neutral alcohol. You can distill it out, leaving behind the salt, and then you can acidify. This is further, this is distilled out first, and then it is acidified. That becomes RCOOH, and then this is again distilled out. It is a higher boiling point. But first you have to hydrolyze, acidify, so that it will be, instead of sodium alkanoate, it becomes alkanoic acid. And then after removing all, Na plus, it was there. Now H plus will be making a covalent bond, and the remaining NaOH will remain. So this neutral RCOH now is ready to escape on distillation from the mixture. But once it is an ionic compound, sodium alkanoate, it won't, because it is an ionic compound. It will not distilled out on distillation process. So the last step is to make acidic hydrolysis to the mixture. After removing alcohol, you have to get back your carboxylic acid. So this is alkaline hydrolysis, and in that method, this is the any kind of fat and oil is the formula is this. Any kind of fat, this is triglyceride of, you know higher carboxylic acid, or starts from C11, C13, C15, C17, C19, C20, a long chain carboxylic acid. And the nature has created this. This is glycerol, CH2OH, CH2, CHOH, CH2, glycerol, and nature has prepared a triester. This is one ester link, this other ester link, third. And when this is subjected to hydrolysis, alkaline hydrolysis, you get, HONA. I'm writing in a very crude manner because salt will be produced here. And that is soap. The salt itself is soap. And neutral glycerol will be the byproduct. So you have to remove the glycerol, the first you have to separate the glycerol. This is glycerol, or you can call it, what is the IUPAC name since you are studying alcohol? Can you name this compound? Because we have not named dihydric alcohol, trihydric alcohol. In the process, we will be also naming them. What is the name of this compound? What we popularly call glycerol. 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 And funnily, we used to call it glycerine also. It's a very household name is glycerine, but its commercial name is glycerol. What its IUPAC name? Yes? Anyone?
Sir, propane triol.
Huh, no, no. Propane triol khali koile habani. No.
One, two, three, triol.
Yes, 1, 2, 3 triol. It is propane 1, 2, 3 triol is called glycerol. Since we are studying alcohol chemistry, so sometimes I'll ask you to name it officially. And then, in trivial system, and trivial, I mean, in semi-trivial or trivial system. So this is why it is called saponification of ester. Then the fourth point is a reduction of aldehydes and ketones. Aldehydes, ketones, carboxylic acids, and esters. All of them produce alcohols. And the best reducing agent is La. Lithium aluminum hydride is the best choice. I'll tell you many other reducing agents and their limitations also. I'll tell you, but La is the best choice for aldehydes and this carboxylic acid and ester. Now, what happens if you take aldehyde and I'm showing, no, I'm not showing you the mechanism. La followed by hydrolysis. Usually people don't write, or sometimes you can write H3O plus, no harm, but there is no necessity. Just water will be enough. I'll show you the logic why. So to understand what happens, not the mechanism, two hydrogen, one comes here, the other goes there, and it becomes RCH2OH. So ultimately, aldehyde gives a primary alcohol. Aldehyde gives primary alcohol. But if you take ketone, do the same thing, La lithium aluminum hydride followed by hydrolysis. I'll tell you why hydrolysis step is important. I'll show you the mechanism. So one hydrogen here, double bond gets broken down. So this is a secondary alcohol is produced. But if you take carboxylic acid, you take just like aldehyde, you get you need 4 hydrogen to balance so that this part becomes water and this part becomes secondary alcohol. Sorry, primary alcohol. So primary alcohol is the product from both aldehyde and carboxylic acid. And here you get an additional product, water. Same law followed by hydrolysis. And even if you take ester and do the same thing, it will take also 4 hydrogen. This nascent hydrogen concept is a obsolete concept, but we write for balancing purpose. The mechanism is not a nascent hydrogen atom that is responsible. Instead, hydride ion, because lithium aluminum hydride produces hydride ion, And that hydride ion is the nucleophile for the acyl substitution that we have not yet studied thoroughly. I've shown you a glance, I mean, given you a jhalak of acyl substitution during acidic hydrolysis of ester. But we will be doing in an official manner systematically in our carboxylic acid chapter. So there will be two alcohols here. The alkoxy part will give one alcohol. The carboxy part will give you always the primary alcohol, but the alkoxy part will give a variable alcohol. Depending on R dash, 1 degree alcohol is a must, and this is variable. Depending on what is R. Depends on R. What happens here? What any aldehyde or ketone or carboxylic acid or ester you take, I'm showing you, La, it gives hydride ion. In not a direct hydride ion, it comes from La as hydride ion during the mechanism, and it produces O minus. So you have to have, and this H is bonded here, you have to have water. Some people write H3O plus, that is okay. But even water can make it neutral. And because you see, this is alkoxide ion, this is OH minus ion. So alkoxide ion is a stronger base than OH minus ion because alcohols are weaker acid than water. So this is possible. But if you take water, that is also equally good. So there is no strain. Alcohol and water, they are very close in their Kpk values. They're very close. But yes, it is possible. Protonation of the alkoxide ion can be done by adding water. But it is better if you take H3O plus. Add some extra acid so that you can protonate the alkoxide ion and get a neutral alcohol. Now, leave a space, leave a space to write the details. Now I'm showing you sodium. If you use sodium alcohol as reducing agent for this purpose, then that is applicable for ester alone, the last one, ester alone, not for the other three. And that is a special name, Bobelt blank reduction. You can use zinc hydrochloric acid, sodium amalgam water, sodium borohydride, these two for all. Sodium borohydride has a restriction, not for carboxylic and acid and ester. It is only applicable for aldehydes and ketones because the bond is so covalent, the ionic character is so less. The hydride ion comes with much difficulty, so that since carboxylic acid and derivatives have very low electrophilicity in the carboxy carbon, there is an inbuilt resonance there in all the carboxylic acid and derivatives. So the electrophilicity of the carboxyl or carbonyl carbon or carboxyl carbon is very, very less. Therefore, it is difficult to carry out nucleophilic acyl substitution. You have to drive the equilibrium to the right by removing one of the products, and then remembering the Lee-Satelier's principle that you are driving the equilibrium to the right, because it's not happening spontaneously unless you remove the product. Because carboxylic acid carbon, that carboxy carbon has very limited plus delta character. Why? Because the OH, NH2, Cl, all these, they play a resonance role, and your delocalization of electron happens, thereby reducing the electrophilicity of that carbon. So therefore, we do it with much difficulty, but we do. Therefore, and then sodium alcohol, what we call the Bobelt blank reduction, I'm repeating here, is an alternative reduction for ester alone. I'm repeating here. For aldehydes and ketones, I'm repeating here, sodium borohydride is taken in alcohol medium. And yes, for carboxylic acid and ester, you can use sodium borohydride. I found in some question, is it possible that sodium borohydride ever can be used for carboxylic acid and ester? Yes. In a very restricted condition using aluminum chloride in diglyme, that will be the catalyst. And aluminum chloride is the catalyst. And the solvent is diglyme, 2,5,8 trioxanonane. Trioxanonane. In between, there will be 3O. Oxa means O. So there, this is a very special case, so don't use this for ordinary general purpose. Hydrogen metal, hydrogen gas and any other transition metal like nickel, palladium, platinum, rhodium, ruthenium, these will also can be used for all. Diborane in THF can also be used for all. The only sodium borohydride in alcohol has a restriction only for aldehydes and ketones. Sodium alcohol, the bobbled blank, has restriction only for ester. So you write down this, and zinc HCl and sodium amalgam water can be used for all. So you write down this at home. Now I have written here La and sodium borohydride, they are brothers. This elder brother is La, sodium borohydride is younger brother. Works with the nucleophilic addition mechanism for aldehydes and ketones. I'm not talking of carboxylic acids. Previously, I was referring to a carboxylic acid thing. But for aldehydes and ketones, it is nucleophilic addition which we have not done. It is the hydride ion is the nucleophile. La ether treatment is followed by actually I have not complicated by writing ether. But sodium borohydride works in alcohol medium, but La is usually taken in ether like THF, tetrahydrofuran. So I'm not writing to complicate, to so very messy. So La ether treatment is followed by always water to get a neutral alcohol. You can also add H3O plus. Sodium borohydride works with alcohol solvent, so protonation occurs from the solvent. No need of adding water. The alcohol is a protonic solvent. It's a protonic solvent, so no need like water. La is more powerful than sodium borohydride as the polarity of ALH bond is higher. The hydride ion can be let loose easily. Sodium borohydride cannot reduce carboxylic acid and esters. Now I'm showing you the mechanism. The hydride ion is let loose easily from this actually lithium aluminum hydride LiAlH4. This is a complex hydride ion attacks. Actually, the hydride ion attacks. And this is nucleophilic addition. I was talking about carboxylic acid and derivatives. That is acyl substitution. This is nucleophilic addition. That's the difference. And then you protonate it. Simply by adding water, you can protonate OH and OH minus ion will go. So, yeah. Conclusion that also you mention in your copy that aldehyde gives primary alcohol, ketone gives secondary alcohol, carboxylic acid primary alcohol, ester gives primary alcohol as one product, and another alcohol is variable. It may be primary, secondary, tertiary, depending on the structure of R. Then we go to other points. Before that, let me give you SAQ. Uh, mm, you give only the measure product. I have not given A plus B. I've given one later means you have to give the measure product. If at all, there will be some competing product. I mean, some not byproduct. If it is ratio selective, you get two products. one in larger quantity, the major, the other one minor. La means lithium aluminum hydride. And I'm watching all of you are quite alert. I can feel your presence. Ansul, Rudra, Sami, and Shruti Shreya. They are alert because like the teacher can have a feel, particularly those guys like you who can wake up so early in the morning to attend class. So I need not have to see them to teach. Raise your hand, please. Who has once you complete it, indicate by raising your yellow hand. Guys, I'm in a mood today to compensate the loss we have incurred last time and other times. I'll go fast as well as I will go up to 6:45. So my sincere request to those who will be leaving, I will definitely give you permission. But please watch the remaining part of the video and write down accordingly. Well, let us have a target to complete the whole organic part of class 12 in July. It will be a huge target, no doubt about it, but we can do it. We can do it. You know, Rudra, you are diplomatically silent about the exam, which I think others like Samidha had pointed out, or someone had pointed out. But Rudra is diplomatically silent. Now, Rudra, you did point out. Who pointed out about the missing of one test that we scheduled for maybe last Sunday? Yes? कौन थिला ऑर्गन दीटा देखो केमिकल काइनेटिक्स एंड केमिस्ट्री जो दीटा देखो थिला तुम चुप है कि बसी गलो रुद्राणी आई एम सॉरी रुद्र आगुर टे रिमाइंड करबा कथा तुम जानि छ सब जिंस यू रिमाइंड मी you know the rules and regulations because here we are the real kind of teacher and taught you learn something and you are also responsible to remind me. So you didn't remind. Gotte ke bade Samidha ke someone, maybe Shreya Shruti, I don't know. Maybe Shreya Shruti, I don't remember. ଖାଲି କହିଲା ପରୀକ୍ଷାଟା ହବନି କିଏ କହିଲା ଶ୍ରୁତି ତୁମେ କହିଥିଲ କି ଶ୍ରୁତି ଶ୍ରେୟା
Yes, sir.
ତୁମେ କହିଥିଲ
Yes, sir.
I faintly remember. They reminded. They means the two sisters. But no one else. They remained diplomatically silent because these two chapters are, hardcore physical chemistry topics. Chemical kinetics is more geometry and mathematical based, while electrochemistry is more concept based. कौन रुद्र खराब लगुची केबे करिवा
A Sunday?
रेडी
Yes, sir.
Samidha, what about you? Ready?
Yes, sir.
Okay. Coming Sunday, aji hela Gurubar. Today is Thursday. Yeah. And Sunday, evening 6 o'clock. As usual, we'll be conducting a test, so you revise. You have left. Kar hela? Hath deko? Rudra hela?
Yes, sir.
Rudra. Au kar hela? ଏଇଟା କ'ଣ କହିଲ
Sir, aldehyde baniva CH3CHO.
yes because triple bond gets hydrolyzed by water in presence of mercuric salt. We write mercuric sulfate, sulfuric acid, heat. Of course, mild heating 60 to 80 degree is required. I should have written, but once I write mercuric salt and water and acid, it will, H, OH, as you know, H will be coming here and OH will be coming here, and this is enol that will quickly tautomerize to give you, I'm not showing the mechanism here, CH3, C double bond OH. So acetaldehyde is A. And now we learn that a carbonyl compound or a carboxyl compound will be hydrolyzed by La, will be reduced by La, followed by hydrolysis to produce, since it is aldehyde, what is B? Yes,
Alcohol.
Ami, what is B?
The CH3COH.
कौन CH3COH एसिटिक एसिड ना कौन कौच
No, sir. CH3COH.
कौन CH3COH ମୁଁ କିଛି ମା ବୁଝି ପାରୁନି ଆଉ ଥରେ ଟିକେ କହିଲ CH3 I am not
C.
able to hear properly
Sir, OH.
OH କଣ CH3OH ମିଥାଇଲ ଆଲକୋହଲ ଗୋଟେ କାର୍ବନ ଉଡ଼ିଗଲା
No, sir. CH3COH.
CH3COH ର ମାନେ କଣ ମ yes ଶ୍ରୁତି ଶ୍ରେୟା
CH3CH4.
OH yes CH3 CH2 ମଦ ଏଇଟା ହିଁ ମଦ ୟସ୍ ଏଇଠି ଗୋଟେ ହାଇଡ୍ରୋଜେନ ଲାଗିବ ଏଇଠି ଗୋଟେ ହାଇଡ୍ରୋଜେନ ଲାଗିବ ଏବେ ଆମେ ପଢୁଥିଲେ ଇଟ୍ ୱିଲ୍ ବି ଗିଭିଂ ୟୁ ଏ ପ୍ରାଇମେରୀ ଆଲକୋହଲ ଇଥାନଲ ହେଇଛି ବୁଝିପାରୁଛୁ
Yes,
ଅଂଶୁଳ
sir.
ଅଂଶୁଳ
Yes, sir. Yes.
so B is ethanol and what is C? It will give you a sodium salt goes
Sodium
without
salt.
saying sodium ethoxide O minus Na plus now the question for D Shruti Shreya what will be D? Will it undertake Williamson synthesis of ether or Rudra? What?
Sir, elimination.
What will be the product then?
Sir, ଗୋଟେ alcohol ଆଉ ଗୋଟେ isobutene.
Isobutene. I was interested in that. Yeah, of course. I can write E here because here the only product formed will be elimination product. So this will be removing a beta proton and this will be giving you 100% this and this once again this alkoxide will become ethanol ETOH I'm writing. So not you carry out Williamson synthesis to give you ethyl tot butyl ether. No, that happens when if you want tot butyl ethyl ether, then you have to take a tot butyl alcohol, make it sodium salt, sodium tot butoxide, and add to that ethyl chloride. Then it will be giving you the substitution product. The substitution के लिए आप जानते हो 1 degree is the best choice. 2 degree there is again mixing up. So 1 degree there will be strong base, there will be substitution, major product. Elimination will be very, very minor. So, कार सब ठीक अछि? Raise your hands, please. Okay. Now the fifth method of preparation is from primary amines. 1 degree amine. Alcohols can be prepared just, I'm not showing you the mechanism here, it's very little involved. A nitrous acid from amines with nitrous acid, HNO2. Nitrous acid is never marketed. It is prepared in situ, which is unstable. In situ, by taking a nitrite salt with dilute hydrochloric acid, and that will give you HNO2 in situ, and that will, I'm showing you in a very schematic manner, NOH and double bond O, so that nitrogen gas will escape and N2 you will escape and water. So you get back alcohol. Are you writing?
Yes, sir.
Yes,
Yes.
sir.
And this goes by SN1 mechanism mostly because uh, once you treat it with HNO2, you get just like I showed you there in the preparation of chlorobenzene by Sandmeyer's reaction, starting from aniline, then benzene diazonium chloride. The similar manner, this is not benzene, alkyl diazonium chloride will be formed, and that is unstable. Benzene diazonium salt is stable, but this is a very very unstable intermediate, very very unstable, and that vanishes. You know what happens? This immediately vanishes, escaping nitrogen gas, and you get R plus, and then it is attacked by water, and then removal of H plus, that will give you a neutral alcohol. After removal, after deprotonation, you get alcohol. So it goes by SN1 process, accepting, you know, ethanol, ethylamine, and methylamine, where you do not expect 1 degree carbocation to be stable. Others, they go for rearrangement, give a different product. You know, this method also gives rearranged products. That is a proof that the reaction mechanism is SN1. From methyl and ethylamine, the reaction is slow, and you get varieties of other products. In methylamine, actually the major product is methyl nitrite, ONO. ONO. Methyl alcohol is the minor product. In yes, ethyl chloride or bromide, ethylamine, ethylamine, ethyl alcohol is the major product along with some other minor products. But in methyl amine, people write, oh yeah, NS2, they write NaNO2HCl, they write a methyl alcohol, but actually this is minor product. Sorry. Of course, this is minor, this is major. Nitrite, ONO. Because the SN1 mechanism, doesn't operate, SN2 comes into force in this case in ethyl alcohol and methyl alcohol. In that case, methylamine and ethylamine, not SN1, SN2. So HNO2 attacks from the oxygen center and produces ONO, nitrite. This is methyl nitrite. Methyl nitrite, not nitromethane. So remember this, methylamine will give you the major product as methyl nitrite, not methyl alcohol. Then coming to the sixth point, hydration of alkenes. This we have already done in details in our alkenes chapter. Done. Of course, acid catalyzed. I will give you an example to remind you that we have done. Another example. I am not doing any hydroboration, oxidation, nor oxymercuration, demercuration. I'm simply doing, hydration with a havoc, with a lot of changes happening. Unless you make the mechanism restricted to a cyclic one, and not allow carbocation to be formed to show its heroism. Just this will give, the measure product, say D. No, so ring is so unstable, the angle strain is so high that it will definitely try to relieve. But five-membered ring is not that unstable. It is little less stable than six-membered ring, but it is not that unstable like three-membered and four-membered rings. So do it and just you there, you want. Yes. क्या हुआ तेरा वादा, ये कसम, ये इरादा। आखिरी दिन होगा, क्या हुआ तेरा वादा, ये कसम, ये इरादा, ये कसम, ये इरादा, भूलेगा तुम। ये दिन जिंदगी का आखिरी दिन होगा, क्या हुआ। अरे कौन वो रुद्राणी, दिस इज वेरी अनफॉर्चुनेट।
Sir, second tare
फास्ट कुह मो,
cyclopentanol.
फास्ट इज फास्ट, सेकंड इज सेकंड।
Mhm.
अंशुल कौन कौच की
No, sir, Samedha.
ସମିନାନୀ କ'ଣ କହୁଛ?
Sir, 1-methyl cyclobutane 1 habo.
Precisely one of the products. This is a 3-degree carbocation, but 5-membered ring has some it will undergo from sp2 to it will remain as sp2. Carbocations are sp2 hybridized, so this is a 3-degree carbocation. Once H plus is added here, H is added here, plus will be added here. So as Miss Samita has rightly pointed out, one of the products will be this, but this is one of the products.
Sir, B ଟାରେ OH ଜାଗାରେ H ହବ.
Huh?
Sir, B product ଟାରେ OH ଜାଗାରେ H ହବ.
ନା ନା OH ଟା କୋଉଠିକି ଆସିବ ଏଠିକି ତଳକୁ?
No, sir, OH ମୁଁ sir structure କଥା କହୁଛି. ଏମିତି ring ହବ, ତାପରେ first ଟାରେ methyl group ଥିବ ଆଉ ଗୋଟେରେ H ଲାଗିବ.
Yes, Rudra.
Sir, ring expansion haba?
Ring expansion, how it will happen? Here out ହେଇପାରିବନି, ଏଇଠି ହବ. You are thinking rightly. Had I given a double bond here, ଦେଖ mechanism କେମିତି ଯାଉଛି ଦେଖ. I am showing you the mechanism which Samidha got a little bit confused here. H plus ion first is protonated. So this H comes here, so that plus comes here. CH3 is here. So there is no how can the bond break unless there is a driving force? Had there been a plus charge here, then of course you can say that there is a possibility of hydride shaped. Can it? Yes, this happens in one go. This happens in one go, not that primary alcohol, a primary carbocation is ever formed. Supposing you understand by a hydride shift here and you bring this for understanding purpose, it happens in one go. So this happens, and then the ring expansion can occur so that you have a 6-membered ring. With supposing we call it 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and the detachment is from 2. So 2 will be now carrying plus charge.
Or
Now S3O plus, S2O will be the nucleophile, and then removal of H plus will give you cyclohexanol. So the other product is cyclohexanol, but this would have been more easy had it been double bond would have been here than here. Immediately you will write. Then what will happen in the second question? I told you that in the second question there will be almost one product, although a 1-degree carbocation is not formed. So the driving force will be ring expansion. You just think that the 1-degree carbocation is formed, not 3-degree. So here, supposing you think that this will be CH2 plus, and then ring expansion will happen. The same manner, the plus charge will come here, and then water and H minus removal, H plus removal will give you cyclopentanol. Same thing will happen in 2 steps. So but it's not the major product here. This one which Sami told is the major product, because this is difficult. Because once 3-degree carbocation is formed here, and it is not that very unstable 5-membered ring, OH will be joining there, water and removal of H plus will be happening there. But ring expansion, though it is more stable as a ring, but you have to go for the another hydride shift process, and then you will go for ring expansion cyclohexanol. But yes,
Sir, beta cyclo 2-methyl cyclopent pentanol haba?
आर पटे OH ଲାଗିବ
Yes, sir.
आर पटे OH କେମିତି ଲାଗିବ it is addition reactions are regio specific elimination reactions are regio selective so ଏଠି 3 degree carbocation ହେଲା ମାନେ ଆଉ question of 2 degree carbocation doesn't arise ସେଇଟା elimination ରେ ହେଇଥାନ୍ତା କିନ୍ତୁ addition ରେ ହବନି yes elimination addition ରେ ring expansion ହବ ଯଦି strain ଥିବ ring expansion ହବ are you following me
Yes, sir.
ହଁ ତମେ ଯୋଉ କହୁଛ OS ଟା ଏଠି ଲାଗିବ AS ଟା ଏଠି ଲାଗିବ ସେମିତି ହୁଏନି addition is not regio selective it is regio specific okay so this plus cyclohexanol no doubt cyclohexanol will be formed and this in this case the only product will be cyclopentanol because this of course very minor you can write down OH here and CH3 here, no doubt about it. But that is minor, much minor. But this will be the major one. But this one, in this case, it is very difficult to say unless you go to the data which one will be major, which one. Maybe in near equal yields it will come, it will appear. This five-membered ring has not much different in little strain is there, but not as much strained as four-membered and three-membered rings. Okay, then we go to the other point. Seventh point of preparation of alcohols. Seventh point is hydrolysis of yes.
So I have another
Yeah,
question.
yeah, 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 yeah. Please proceed. Hydrolysis of
Thank you.
ethers. Now, please, you can leave whenever you want without my permission. I give you full permission to leave. I will not mind at all. Now, see, this is ether. It's very simple. You treat it with dilute sulfuric acid. That means H3O plus. You get 2 ether. If it is a non-symmetrical ether, 2 alcohols. If it is symmetrical, you get 1 alcohol. This is very simple. And it not same. Mechanism is same. You know, this is SN reaction will happen. First, there will be protonation. It will be alkoxy group will be protonated. And then we will study in details about this process in ether chapter. The detailed mechanism of hydrolysis in ether chapter. Don't let us wait for that. Then the eighth one is from Grignard reagent. This is very important, very, very important. As you know, the alkyl magnesium halide can be easily prepared from alkyl halides by just putting magnesium in presence of ether and living overnight. There will be a reaction, then carbon halogen bond will break, carbon magnesium bond will be established, and halide will be coming to magnesium. So you get a compound having a lot of carbanionic character. It has some covalent character, some ionic character, but when it will react, it will go as a carbanion to attack. And so this is Grignard reagent, as you know, Gr. So when Gr will react with formaldehyde, then what happens? This is nucleophilic addition, which will be doing the mechanism in aldehydes and ketones chapter. So you will produce R, carbonyl carbon ray, CH2, O minus. Then there will be another hydrolysis step that either simply water and many literature you write H3O plus because logically simply water will do the job, but H3O plus is okay. Then you get alcohol. So 1 degree alcohol is obtained from Grignard reagent and formaldehyde. This is the requirement. But if you take any other aldehyde, same thing will happen. This is nucleophilic addition, ADN. I will be showing you now how it happens. You take any other aldehyde, then the same, it will go as carbanion, and with H3O plus, I am not writing the two steps. It will become R dash. Supposing this is R dash will be hanging here as a nucleophile, and this CHOH. So you get a 2-degree alcohol if you use any other aldehyde than formaldehyde. Instead, if you take a ketone, लिखुचो ना नहीं?
Yes, sir.
If you take a ketone with same any Grignard reagent you prepare, you take a ketone and carry out the hydrolysis. And this carbanion will attack here, and this will be when hydrolyzed, it will produce a 3-degree alcohol, goes without saying. This C will be attached to this R will be hanging, the nucleophile will be hanging here, and when hydrolyzed, it will be 3-degree alcohol. So the conclusion is formaldehyde will give you 1-degree alcohol, any other aldehyde will give you 2-degree alcohol, and ketone will give you 3-degree alcohol. That is the thing we conclude. Just I can give you one SAQ to say repetition of the same thing. ଏଇଠୁ ଗୋଟେ ଆଉ ଗୋଟେ ଇଣ୍ଡିପେଣ୍ଡେଣ୍ଟ ଦଉଛି. That means A gives B, A gives C also. In both the cases, you will get alcohols, but Grignard reagent will give you an expanded alcohol, and that too, since it is a ketone, will get a 3-degree alcohol. But since it is a ketone, mere reduction with La followed by hydrolysis will give you a 2-degree alcohol. So C will be a 2-degree alcohol, B is a 3-degree alcohol. Karsalla.
Yes, sir.
कौन हला एटा कौन हला
Sir, aldehyde, ketone, sir, propanone.
acetone, right?
Yes, sir.
Or propanone, because this is same. Only acetylene on hydration in presence of mercuric salt, acid will give you acetaldehyde. Others will give you ketone. This is acetone is formed, and if you go in this direction, since it is acetone is A, and our attacking nucleophile is isopropyl carbocation, this one, this will attack from the Grignard reagent, and on hydrolysis, you will get a 3-degree alcohol, because we know that ketone with Grignard reagent will give you 3-degree alcohol. So the 3 groups attached will be 2-methyl and now isopropyl. CH3 whole 2 CS means isopropyl. So you get an alcohol. Can you name this alcohol? And we can't call it isopropyl dimethyl carbinol. This will be a huge fun. So you have to go for IUPAC, where the locant of all will be minimum. So have to go in this way, either this way, that way, 2, 3, 4. So
So,
this 2, 3 dimethyl, then
sir, 2, 2, 3 dimethyl. Oh, sir, yes, sir. Butone.
Shruti se, not
Butanol.
butan. Yes, yes, butan to all. The ANE, that primary suffix cannot be removed. Primary suffix is never ever deleted. The E of primary suffix, that is deleted if you find a vowel O, Y, I, O, U. Y is considered as a vowel because we are deleting E. So it will be 2,3-dimethyl butan to all. You got it?
Yes, sir.
Let me give you another example where, uh, say, we are uh, having this compound and we'll be uh, now, since it is an aldehyde, with any Grignard reagent will give you secondary alcohol. You just attach the alkyl group of Grignard reagent onto the carbonyl carbon and make that double bond O into single bond OH. And then you do, here there will be Williamson synthesis. I've given you deliberately a 1-degree halide. So Williamson synthesis will happen because we are slowly marching towards the chapter ether after phenols.
Yes, sir.
କଣ ହେଲା A?
Sir, ଏ ହେଲା sir ହେଇଯାଉଛି alcohol, secondary alcohol.
Sorry. So এই Grignard reagent ରେ ଯୋଉ alkyl group ଟା ଅଛି, that will be attaching onto the carbonyl carbon. So A will be, I'm just changing the color. A will be CH3 CH CH3
Sir, 2 methyl pentan 3ol.
এইଠି ଝୁଲିଯିବ କ'ଣ କିଏ ନା ଏଥିଲଟା CH2 CH3 ଟା ସେଟା ଝୁଲିଯିବ ଏ କାର୍ବୋନିଲ କାର୍ବନ ଏଇଟା ହେଇଯିବ ଆଲକୋହଲ ସୋ ଏଇଟା ଗୋଟେ ସେକେଣ୍ଡାରୀ ଆଲକୋହଲ ହେଲା ମାନେ ଆମେ ଜାଣିଛେ ଆଲଡିହାଇଡ ଏନି ଅଦର ଆଲଡିହାଇଡ ରୁ ସେକେଣ୍ଡାରୀ ହବ କାରଣ ଫର୍ମାଲଡିହାଇଡ ରୁ ହବ ପ୍ରାଇମେରୀ ଆଲକୋହଲ ସୋ ଏଇଟା ହେଇଗଲା ୱାନ୍ସ ଏଇଟା ହେଇଗଲା ମାନେ ସୋଡିୟମ ଦେଲେ ଆଇସୋପ୍ରୋପିଲ ଏଠି ON ହେଇଯିବ ମାଇନସ ପ୍ଲସ୍ ପ୍ଲସ୍ ଏଠି ଏଥିଲ ଅଛି ସିଧା କରିଦେଲି so the corresponding alkoxide salt ହେଇଯିବ. And then, since it is a primary alcohol, so this will be acting as a nucleophile. to remove this, and we get a huge ether. AIG,
Yes, sir.
O ଲାଗିଯିବ ଏଠି O minus was the nucleophile. O ସାଙ୍ଗରେ ଲାଗିଛି CH ସାଙ୍ଗରେ ଲାଗିଛି CH2 CH3 ଆଉ ଗୋଟେ ଲାଗିଛି CH3 a CH ସାଙ୍ଗରେ ଲାଗିଛି a CH2 CH3 and isopropyl, and it will be a huge ether. We are not now spending time to name this compound. That is why the oxa system came into being. In type of big ethers, so it is always call this as oxa and number the oxygen atom like carbon, and follow the same rule as alkenes. 1 2 3 4 5 6 7 1 2 1 2 3 1 2 3. So we go this way: 1 2 3 4 5 6 7. So it will be better and easy to say 3 ethyl 2 6 sorry 2 comma 6 dimethyl 4 oxa 4 oxa and then heptane, oxaheptane. Because the other name, alkoxyalkane name, will be too tedious. You can do it. Here, make the main chain as this 1 2 3 4 5. So 2 methyl, this becomes, this will be 1 dash 2 dash 3 dash 2 methyl ethoxy. This will be propoxy.
Propox.
Propoxy. 1 2 2 methyl or methyl propoxy, and that will become 3 in between bracket 2 methyl propoxy, propyl, then propoxy. Of course, before that, it will be coming 3 ethyl. Of course, when a complex branch and a simple branch, they share a common word, then the simple branch will come first. 2 methyl will come first. So 3 ethyl, 2 methyl, 3 2 methyl propoxy, then the 1 2 3 4 5 pentane. R2 इससे बेहतर है ये ऑक्सा सिस्टम. That is the trivial name. If you just for fun, if you want the IUPAC software that we are using to name this compound, what he is saying, it will not say anything other than the rule. Let me draw. Oh, sorry. I have to draw this here. ठीक है ना? ठीक है ना? अरे ठीक है कि नहीं?
Yes, sir.
जो कंपाउंड ଆମେ ଲେଖିଥିଲେ ସେଟା ହେଲା.
Yes, sir. ठीक ଅଛି, sir.
Now I'll ask the name, see what this is telling. Whatever we told, ଆଉ ଗୋଟେ ଇଥାଇଲ କୋଉଠି ଆଉ ଗୋଟେ କୋଉଠି ଭୁଲ ହେଇଗଲା କି? ଏଥିଲଟା କାହିଁ କହିଲାନି ସେ? ଓହୋ, ଏଥିଲ କେମିତି କହିବ? ଆରେ ହେ, we are so fools, and I used to say, had it not been a public video, ମୁଁ ଅନ୍ୟ କଥା କହିଥାନ୍ତି. So ଏଇଟାକୁ ପରେ ଆମେ ସେତେବେଳେ ଆମେ ସିନା ଏଥିରେ କରିଦେଇଛେ ଏଥିଲ, ସେ ସିଷ୍ଟମରେ 1 2 3 4 5 ଯାଇଥାନ୍ତା. So 3 ଏଥିଲ କେମିତି ଆସିବ? We are so fools and nobody pointed out. ମୁଁ କହୁଛି IUPAC ରେ କେବଳ 2 methyl will remain, because we will be taking this as the longest chain 1 2 3 4 5. So 2 methyl and then 2 methyl propoxy, whatever is given is correct. Yes. Okay.
Yes, sir.
ତାକୁ ଗଲୁ ବୋଲି ଆମ ଭୁଲଟା ବାହାରିଲା. Otherwise you were dosing ଢୁଳଉଥିଲ ସବୁ. Whatever mistake I make, you don't point out. because I'm in a haste. Okay, now we will come back to the some of I would like to you to write down something, and I will wind up the class today. These two things you already have done: hydroboration, oxidation. In alkenes chapter we have done. We have seen that hydroboration oxidation gives antimarconic of alcohol in two steps. First, BS3THF or diborane THF, followed by the second step, oxidation of the trialkyl borane by hydrogen peroxide alkali. That will give you the alcohol. And that alcohol will be looking like an antimarconic, as if you have added water to the alkene in an antimarconic of way, give you antimarconic of alcohol without any room for rearrangement. Had you taken H3O plus, then it would go via the carbocation mechanism. Then that this is ADE, the electrophilic addition that will undoubtedly make a havoc, change in the position of carbocation, and then the product will be changed. But here there is no rearrangement. And of course, I have told you the stereo electronic, mechanistic way is the same. H and OH will be approaching from the same side, both up or both down, 50-50. Accordingly, you can also look to the stereo specificity of the product. From a stereo specific reactant, you can tell. Oh, okay, I'm just giving you, since let us put a point. Let us put a point. This is the 9th point that we have done. Sorry, 8th point we have done. 8th point, right?
Yes, sir.
This is the 9th point we'll be doing, HBO. What is HBO? A channel. English movie channel. Or it is
Sir, hydroboration oxidation.
Yes. The main point is no rearrangement product, antimarconic of alcohol, and scene addition. And what is taken? The first step, you take B2H6 THF is a solvent, or sometimes you find BS3, because then THF it will break down to its monomer. And the second step is oxidation by hydrogen peroxide in presence of alkali. So that will give you that. Now I am giving you a question. This is a stereospecific reactant. This is, you can call it E, and whatever the name, 1, 2, 3, 3-methyl pent 2-in. 3-methyl pent 2-in. So if you carry out the HBO, that is B2H6 or BS3THF, followed by oxidation by hydrogen peroxide, what will be the product? It's a stereospecific reaction. A particular stereospecific reactant will give you a particular stereospecific product. And I've told you the mechanism is same, antimarconic of alcohol. And no rearrangement. Carbocation is not formed here. It goes by a cyclic transition state. The OH.
Yes, sir.
And H. OH is the negative part, will descend onto the carbon bearing more number of hydrogen, antimarconic of here. and H. I'm not showing you the mechanism. H. Had it been Markovnikov, then OH would have attached here H. But the mechanism is sin. So both will approach from the same side. And the other possibility, the 50% possibility, is the other side. The H will come from here, OH will come from here. So you get two enantiomers. What is that enantiomer that you can? Two enantiomers. One is OH here, and this methyl hydrogen will be stooping down, remaining on the same side. The hybridization changes. So H will be here. This is one, and 50% will be where H, and this will be stooping up. I mean going up, but same side. And OH will be here. So these two are not same. They are enantiomers. If you just make upside down and try to see, they are mirror images of each other, not identical. So you can say, since two groups are same, you can say in terms of erythro pair or trio pair. Can you tell me? When the two groups are same, then you can express that particular diastereomer with the help of the prefix erythro or trio. When the two identical groups are eclipsed, if the non-identical groups are also eclipsed, it is erythro. If they are remaining in the opposite side, then it is trio. Or it is better to say, when the non-identical groups, they are eclipsed. If the identical pair remaining on the opposite sides, then it is trio. If they also eclipse, then it is erythro. So it's come from the carbohydrate chemistry, erythros and trios. So we give erythro-trio term just to specify which diastereoisomeric or diastereomeric enantiomeric pairs is formed. Which diastereomeric enantiomeric pair is formed? Trio or erythro? Yes. If you just make you just make it 120-degree move anticlockwise, then this and this will come eclipsed. At that time, you will find hydrogen hydrogen will remain opposite, methyl methyl will remain opposite. So it is what? It is
Trio.
3OD and L. Yes. Instead of writing RRSS or RSSR, taking a long time to find the configuration, it is better to write 3ODL. You understand? I mean, যদি 120-degree ବୁଲେଇବା anticlockwise, then ethyl ସାଙ୍ଗରେ OH eclipse ହେଲା ବେଳକୁ methyl methyl opposite କୁ ପଳେଇବ, hydrogen hydrogen opposite କୁ ପଳେଇବ. ସେ ସିଚୁଏସନଟା ହେଲା 3O ର. ଯଦି ସେତେବେଳେ ଆଉ ଯଦି ଗୋଟେ ସୁଇଚ୍ କରିଥାନ୍ତେ, you would have started from, no, let me write down, E has given 3ODL pair. So conversely, Z ଯଦି ନେଇଥାନ୍ତେ, Z alkene କ'ଣ ଦେଇଥାନ୍ତା? ଏରିଥ୍ରୋ ପେୟାର. ଏଟା ଆମେ ଲେଖୁନେ. ଆମେ ଇ ରୁ ଆମେ ହାଇଡ୍ରୋବୋରେସନ ଅକ୍ସିଡେସନ କରିକି ଆମେ ପାଇଲେ the 3O pair and Z ନେଲେ ସେଇ ମେକାନିଜମରେ ସିନ୍ addition mechanism you will get erythro pair. Ethyl OH ku same eclipse ରଖିଲା ବେଳକୁ methyl methyl also in the same side, hydrogen hydrogen also in the same side. So this is the high time. And finally 10 is mercuration and demercuration, oxymercuration, I'm sorry, mercuration and demercuration. This, as I used to say, OD, the main is no rearrangement, product is formed, and Markovnikov alcohol is formed. And no rearrangement, that is the main point. Advantage. For example, and the first you take mercuric acetate followed by hydrolysis, and second you take sodium borohydride in presence of alkali. This is demercuration is done by reduction process with taking sodium borohydride alkali. And first step is mercuration, oxymercuration, and then demercuration, giving you a Markovnikov alcohol with no rearrangement. So if I give you a question, here nothing can be done. HG. And followed by 80 लिखी दूची 80 H3O plus 80 लिखी दूची 80 redox जो demercuration टा मध्य 80 कर दूची so that you get এটা তো অলরেডি କରି ସାରିଛ এই ଦିଟାର କିଛି ବାଟ ନାହିଁ କାର୍ବୋକେଟାୟନ ହେଲେ ସିନା ସେ ରିଆରେଞ୍ଜମେଣ୍ଟ ହବ କାର୍ବୋକେଟାୟନ ତ ହବାର ନାହିଁ ତେଣୁ ଏଠି product will be specific. If you want to retain the ring structure, ring size, then you carry out oxymercuration, demercuration, and hydroboration and oxidation to get either Markovnikov alcohol or anti-Markovnikov alcohol. A कौन होगा?
सर ए हबो गोटे साइक्लोब्यूटेन रिंग रे गोटे मिथाइल गोटे OH
ହେଲା
सेम पोजिशन
এটা তো
यस सर
this is Markovnikov addition and this one
सर मिथानॉल ग्रुप टे लगियो
yes you can call it a cyclobutyl methanol or अब कौन से तो cyclobutyl methanol. And here already you have seen what havoc it will create. It will produce cyclopentanol. Okay, nahi?
यस सर
Now see the difference. How useful is OD and HBO? Not to allow any ring expansion, not to allow any rearrangement of the original skeleton to happen. This finishes our today's program. When we sit, thanks to the three girls who are still watching, Rudra and also Rudra. We will be sitting on Saturday again with a long session up to 6:45 to finish alcohols. Alcohols, you know, the properties is more involved. I mean, not involved. Involved means complicated. In literature, we use the term involved to express complicacy. Oh, the situation is really involved, means getting complicated. So that will be involved, means it will have more intricacies and interesting aspects. Bye-bye. Sunday by ready है जाओ.
Thank you, sir.
प्रणाम सर